This is obviously not a neutral compound. It's a charged polyatomic ion. So, first of all, which rules can we use here? Either of these have a specific rule about them? Pardon? Oxygen does, yeah. What's the rule about oxygen? -2, with a few exceptions, and this is not one of those exceptions. So, -2, we have 4 oxygens. Total negative oxidation number of 8. Okay, so what do we have to have here? Remember that it's got to be something that plus a -8 will equal -2. 6. So this is going to be a +6. And then again, divide by 1. So we have our final answer of that. Isn't that messy? It is. The sulfate has got
so
a...
what does this tell us? Like,
what it's... Yeah, that's exactly my beef with them.
Wait, is there 2 minus 2?
Well, yeah, because this is the charge on the whole ion. You know, and if you need to think about it like this, you can. This is the oxidation number on the oxygen within that polyatomic ion. This is the oxidation number on the sulfur within that polyatomic ion.
It's too much.
It's not, it's a pretend charge that helps us think about how they're sharing their electrons. Because they're not transferring them, they're sharing them.
I think I can picture that pretty well with the stuff in here.
Okay, good. Good, because this is a tough concept. This is one that a lot of people really fight with.
This seems kind of pointless.
It does, doesn't it?
Yeah.
We're going to get to the one use of it that you'll have for now. When you get on to college chemistry, you'll come up with some other uses for it. For now, it's useful for naming. Okay, and we'll do stock system naming with oxidation numbers. I know, I don't like them because it feels useless. There are uses for them further down the road, I promise. Okay, so let's do 2 last examples. Ooh, let's get wild and crazy with nitric acid. Whoa! HNO3. What's the big uh-oh with this? There's more than 2. Okay, well, that's fine. Let's start off. So we're always going to start with our most electronegative and things that have specific rules about them if nothing else will work. So, do we have specific rules about anything in here? Oxygen and hydrogen. We're going to start with oxygen. So, we know that oxygen always has an oxidation number of -2 with a couple exceptions. This is not one of those. -2 times 3, we get -6. Okay. Now, what about hydrogen? Is there a rule for hydrogen?
Yeah.
Yes. What's the rule for hydrogen? Yes. Okay. So, we're going to say +1. We only have 1 hydrogen. So that gives us +1. And the overall algebraic sum has to be 0. So we've got x plus 1 plus -6 equals 0. Okay. We've got positive, yeah. So we know that this has got to be a +5. How many nitrogens do we have to divide that up against? Just 1. So we have our oxidation numbers assigned. Let's do one more with multiple parts. Can I erase? In keeping with our theme, we'll go with phosphoric acid. You've probably all consumed it in pop. Okay, start with oxygen again. What's oxygen's oxidation number?
-2.
-2. Times 4, we have -8. Okay, hydrogen has what? +1. Times 3, we have +3. So now we have x plus 3 plus -8 equals 0. We're going to have another 5. So, and if you need to do the algebra here, most of you can do this in your head, but that would be +8 minus 3, x equals +5. We only have the one phosphorus, so we have +1 plus 5 minus 2. Okay? Not hard, just following the rules. So now let's explore the one use we have for this. Remember how I told you that there were multiple naming systems for molecular compounds? And you have learned the prefix system. So in the prefix system, let's pull our PCl5 over here. What is this called? Phosphorus. Phosphorus pentachloride. Under what's called the stock system of nomenclature for these things. And we have to remember that we have these oxidation numbers up here. This is called phosphorus 5